So a sequence also can converge, just like we learned about improper integrals. Converge and diverge, blow up. A sequence has a limit, and it named like this: limit of a sub n equals L as n goes to infinity. Here's a sketch. So I have a data. So that's why I keep saying that it is a pretty important topic, of course. Here's the data. Again, sequence is a list. So how many cats there are in my neighborhood? There were one cat, then there are more, and then more and more and more. Then students moved in, population blew up a little bit. Then students are moving out for summer, population is going down. Then the next semester starts going up, and on average, it does like this. That is interesting behavior. Just like in the kindergarten, they told us connect the dots game. With a sequence, the same thing. It's data is provided. That's a sequence. That's a list of cats, numbers of cats in the neighborhood. When I'm looking at it, I can see that there's a pattern. So what I'm going to do is I will actually draw, like check this out. I do have a ruler. I will see that it is approaching something. So I will draw a line, and I see, oh yeah, no matter how far I count, the sequence approaches some finite number. On the x and y axis, it looks like so. N, this is n, is keep growing. N is a counter, the first cat, the second cat, the third cat, the fifth cat, and so on. But then a sub n is in green dots. A sub n approaches capital L. Where is capital L? This green line is capital L. So the definition says DEF. DEF, again, it means definition. Let's shrink it back. If this limit is finite, or it exists, limit a sub n as n goes to infinity exists. If it exists, then sequence converges to L. Sequence converges, and it's called convergent. Converges to L, and the sequence called convergent. If not, then it diverges or blows up. Do you know, can you imagine the example of divergent sequence? I'll show you one more time. Here's the data, let's put it in blue. So cats, 1 cat, 2 cat, 3 cat, and none of them were sterilized, so they keep recreating, and look at that. That is divergent. Example. Divergent. So the data does not seem to be stabilization of the data. That's the representation of the convergence. What do you think about this? Not too bad. Intuitively, I think it makes sense. And we're going to teach you all the methods to find convergence and divergence. And convergence to what? Should I move on, or you keep writing? Dots, 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 very fast. Okay, good. Theorem. So all of this is going to theorem. How to know that the sequence converges. Again, stabilization means stability. You can work with the sequence. It's not going to blow up. So how to know? If a function f of x, let's do limit. If limit of a function f of x is finite, it has L, x goes to infinity. We learn limits in calculus 1, but what it has to do to the sequence, this is a function. We don't talk about functions here, we're talking about sequences, which is a list. Well, let's match them. And that's a very cool new idea. And at n number, it matches with the dot of the data. I will show you in a second what it means. This is pretty cool new idea. And I'll write in parentheses, which means where n is integer or a counter, remember? Integer. It's a counter. It's a dummy variable that counts. Then f, then the limit of the sequence as n goes to infinity will also be L. So I would say, No, it's actually good enough. This is how the theorem looks like. It looks very dry, but I will show you on the picture. You will admit it is actually makes sense. And again, it's so interesting that we hit calculus 2 class, but we're actually doing what we did in kindergarten. We're connecting the dots. But this time we're doing it in a very grown-up mindset. We actually know what we're doing. And we know the goal. The goal is to figure out if this data has a limit. So let's see, again. Dots, 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 dots. Maybe even did one more heel, and then it does like this. From visually, you look at this and you say, I can see it has a limit, and there's a height over there. Oh yeah, I can see there's a limit. Well, how do you know though? How would you explain to someone that you see the limit? If I'm zoom in and only see 3 dots, I don't see a limit. Who knows what's happening after or before? So how do you know that there is a limit? The mathematical idea here, you connect the dots, just like we did in kindergarten. You connect them with the function. Look at that. Now green part is the function. Let's call it y equals f of x in green. But we know how to find limits for functions. We learned in calculus 1 class. You find the limit, use L'Hopital's rule if you want, use substitute, what we did, common denominator, multiply by conjugate, all this kind of stuff. What is limit of e to the x? What is limit of x squared over x5 to the 7 plus 9? And stuff like that. When you find the limit of the function, and if you claim you connect the dots, and connecting the dots means exactly this phrase. Oh, actually not this one. The connecting the dots means the phrase in dark blue. Here it is. At n, you connecting the dots. So a sub n are dots. F at n is a function. But at the part n, they match. Then you can claim, yes, the limit for f of x will be the same as the limit for the blue dots, which is a sequence a sub n. Let me write it down. A sub n is a list of data, or just a list. Y f of x is a function. You connected them by making an equal sign between them, blah, blah, blah. So that's kind of the idea. What do you think about this? Does it make sense? Connecting the dots. Because you know, from a mathematical point of view, when you see something, you cannot justify it by seeing it. I see it goes flat like so. Well, so what? I don't trust your vision, first of all. Second of all, we're human beings. What if you see only this picture? Then there is no limit. See, it's actually keep bumping up and down, up and down. Limit at infinity means keep looking at the pattern, like so. And that is very important. You need to have a long run behavior in your data, in enough data in order to see the pattern. Just like with the creation of the universe. If you only have like 500 years, that's nothing. What can you claim from that? That's not enough. So in long run means I don't trust your eyes. You need to use computer or math. Math is better. Pure math is better because that one can go to infinity, infinitely many years if needed. Why are we doing all of this? Example. Let me show you a couple examples. So I will give you a sequence, SEQ, a sequence. A sub n is given specifically like so, 19n plus 20, all over 15n plus 16. And then we're gonna choose n to be from 0 to infinity. Again, I can do n from any other number, just make sure we don't have division by 0. Find limit of a sub n as n goes to infinity. Solution. This is what your homework is about. The first homework is very pleasant. It goes fast usually. So, limits for sequences. We just learned sequences. We only know one tool how to work with limits for sequences. You instead check the function. So you say, well, you don't have to say well. I just like saying it. There's a function f of x that can be written as 19x plus 20 all over 15x plus 16. And kind of I know how to find limit for that. And limit of this function, 19x plus 20, 15x plus 16 as xx goes to infinity is known from calculus 1 information about limits. What is the limit? 19 over 15. Do you remember that? Find the leader of the top, 19x. Find the leader of the bottom, 15x. So the limit will be 19x over 15x. The answer is the ratio of the leading coefficient. That's the behavior of the polynomials in the long run at infinity. Not n, it's x. So the limit for the function is known. Then you say by the theorem, then by the th is a theorem. Sometimes we call it somehow, sometimes say theorem 1, sometimes theorem Fibonacci, or whatever theorem is, Cauchy theorem. A sub n, which is 19n plus 20 all over 15n plus 16, also has this limit, which means it converges, this is a nice notation, converges, just an arrow, to 19 over 15 as n blows up to infinity, n as the counter. Let me stop here by a second, lots of writing. This is one example. It's also example from your homework and exam 2. So let me make it very clear. Why do we care between the function and the sequence? That's one thing I need to explain to you to make sure we understand. What is the difference between n? Let me change the color. What's the difference between n and x? Who cares? Well, let's see. N can be only 0, 1, 2, 3, 4, 5, whatever. It's a counter, it's an integer. So actually I can write down the terms of this sequence. When n is 0, what's the first term? 20 over 16. Remember from the previous class, n is 0, 20 over 16 are my first term. What's the second term when n is 1? 39 over 31. Amazing, good job. When n equals 1, and so on. I don't want to calculate more. This is the list of numbers, a list of numbers. How about the function? The function can have x equals 0.17, x can be pi, e. Those are some irrational numbers, square root of 2. X can be minus 0.1700, so it's not a counter anymore. That's exactly what I'm talking here. List of data is just looks like so, and it follows the counting 1, so 0, 1, 2, 3, and so on, 4, blah blah blah. While the function doesn't need a counter, the function can have kind of different numbers, maybe even irrational numbers like square root of 2 or pi. That's the difference, and that's why it's, as you can see, it's continuous. It doesn't have gaps. What is between 3 and 4? Lots of stuff between 3 and 4. You see? Pi is also between 3 and 4. So that's kind of the idea here. Instead of working with a sequence, we choose to work with the function. Functions we know pretty well, increasing, decreasing, maximum, minimum, limits, left, right, asymptotes. We know how functions behave. We found the limit for a function. The theorem says, well, it will work the same way for the sequence. Does that make sense? What do you think? What do you think about that?